Good morning. We return today to integration by partial fractions. We're going to be concentrating on this case, the case where the denominator has repeated linear factors. A repeated linear factor may be any factor that is linear, so of the form ax plus b, but has an exponent here that is larger than 1. We already learned in our last lesson how to handle it when the exponent is 1. So the value of n determines how many fractions you will need to handle that term. So for example, if n is 3, then there will be 3 partial fractions. The denominators would have exponents of 1, 2, and 3 respectively. Up top, there will be a single letter. Okay, so let's begin with a first example. When we're handling these problems, we want to make sure the denominator first is factored. In this case, there's a common factor of x squared that needs to be removed. So we now have this. It's the same as having just a 1 in the numerator. The differential here is dx. We have a linear factor here. This term is considered to be a repeated linear factor. So it is x, which is linear, with an exponent n equals 2. So we will need 2 fractions just for this one term, one more fraction for x plus 1. So it's going to look like this. We're going to have a denominator of x, a denominator of x squared, and a denominator of x plus 1. Okay, like that. So those are our 3 fractions. In the numerator of each will be a single letter, so A, B, C, like that. So instead of trying to integrate this, we will integrate each of these terms. Okay, so the new bit now for today is here. Treat this as the linear factor x with an exponent n equals 2. Therefore, we require 1, 2 fractions with exponents of 1 and 2 in the denominator respectively. Okay, now this is that step where we picture moving to the common denominator. So we can try that here. So the common denominator would be this, of course, x squared times x plus 1, like that. Okay, the original integral can be rewritten like this, as I was saying, with just 1 in the numerator with the dx here to the side. Okay, so now we need to figure out this numerator. So we take a. Now currently it has an x under it. If it is moving to this denominator, it needs to be multiplied by 1 more x and an x plus 1. We will now have plus b. Under it currently is x squared, so this whole part is accounted for, so it needs simply an x plus 1. Lastly, plus c. What will we multiply c by? It has x plus 1 under it currently. It requires the x squared. From this expression, we get that equation which will allow us to solve for a, b, and c. So what do? We take the numerator of 1 and set it equal to this new numerator containing the 3 letters. We now write down what our roots would be. So what values of x would make these denominators equal to 0? Well, 0, right, would make these denominators equal to 0, and -1. And now you see the big difference between this method and the method of unique linear factors that we looked at last day. In this case, I have only 2 roots to substitute, but 3 letters. So I do not have enough roots for the number of letters. And that did not happen in our last class. We had in our last class exactly enough roots for the number of unknown letters. So we're gonna need another skill beyond this. But let's begin with this. So we substitute x equals 0 on the left side. It will stay 1. Now on the right side, if I substitute 0, of course it will be a times 0. Plus b times, so we're substituting 0, so that will be 1. Plus c times 0. So from this equation, we get b times 1 is 1. Therefore, the b value is 1. Substitution of -1. The left side will not change. It stays 1. If I substitute -1 here, I am going to get a times 0. Plus b times 0 plus c times, now it's -1 all squared, okay, which is actually 1. So we have 1c is 1, and that means c is 1. Now, we did not figure out the value of a. What we could do at this point in time is substitute any arbitrary value that we like for x, since we know 2 out of the 3 unknowns. Okay, so we can go back into our equation knowing that now b is 1 and c is 1. So we're going to have a 1 here and a 1 here. And arbitrarily, so I'm going to write here arbitrary, so you know that you can pick any value you like. Normally the easiest one to use is 0, but we've already used that up. So another nice one to work with is 1. So we're going to substitute 1 throughout for x, and that will leave a as the only unknown. Left side stays 1. We're trying to solve for a. We're substituting 1. So it'll be like this. A times 1 times 2. Plus, now we're here. We have 1. We're substituting 1. So 1 plus 1, 2. And at the end, 1. We're substituting 1. So it's 1 times 1 squared. Okay, from this equation, we get 1 is 2a plus 2 plus 1, or in other words, 1 is 2a plus 3. We're isolating a, so subtract 3 first. -2 is 2a, and then to solve for a, divide both sides by 2, and we will get a is -1. These 3 values are now substituted into this equation, and we will integrate each term. So we have -1 over x plus 1 over x squared plus 1 over x plus 1. Okay, so I substituted -1, 1, and 1 respectively. Now, this is also different from our last unit. In our last unit, all of these, once integrated, were common logarithms. And that's because all the terms in the denominator had exponents of 1. But that's not going to be the case when we have repeated linear factors. In particular, right here, we have an exponent of 2. So, how do we integrate 1 over x squared? Well, you guys know that we write it this way, x to the -2. And then we use our integral rule. So we are going to be adding 1 to the exponent and then dividing by that new exponent. So that's what we're going to use for the middle term. The first term is a common logarithm. It's -1 times the ln of x. The second term, once integrated, looks like this. Here, we could write it -1 over x. The last term is also a common logarithm with a coefficient of +1. Constant of integration will follow. Now I'm going to combine the logarithms here. So I might want to change the order of the terms like this. And then to combine these logarithms, we use our properties. If we have a difference in logarithms, we combine and we get a quotient in the argument. So the result will look like this. X plus 1 will be over x. And it's nice if we can remember those absolute value signs. Okay, that was example 1. 2 more will follow.